At the end of the last video, we came up with a solution that was 0.1 molar in benzoic acid and 0.1 molar in sodium benzoate, and we decided this was a buffer. And buffers resist pH change. You can add a little bit of acid, you can add a little bit of base, and this pH will stay more or less constant. And we want to learn how to do those kinds of calculations. And so we pursue that here. Let's start by just looking at the slide from the end of the last video. So here it is. It was benzoic acid plus water makes H3O plus and benzoate. And we did the calculation. We started with 0.1 molar of benzoic acid and 0.1 molar of sodium benzoate. And we did the calculation, and look now how it turned out at the bottom there. We tabulated all the concentrations, and the benzoate is still 0.1 molar, and the benzoic acid is too. So they didn't really change their concentrations much. You can see the amount by which they change is X in this calculation, and X is really, really small in this case. And not only is it less than 5%, it's only 0.065%. It's teeny tiny. Okay, and we attributed this to the common ion effect. The presence of the benzoate, for instance, inhibits the dissociation of the benzoic acid. The presence of the benzoic acid inhibits the reverse reaction, so essentially they're locked against each other. Neither one can change very much, and so in these calculations you find this with buffers. If you mix a solution that's 0.1 molar and 0.1 molar, it remains so, and that's a characteristic of these kinds of solutions. Okay, and the pH turned out to be 4.19. What we want to do now is see what happens if we, add some strong acid or add some strong base to this. So here is just the previous setup. This is what we had to have to start with. 0.1 and 0.1, and the H3O plus ion concentration turned out to be 6.5 times 10 to the minus 5. So now, here's a key point. When you add strong base to a weak acid, it reacts completely. Okay? And if you add strong acid to a weak base, it reacts completely. For instance, when you just took benzoic acid and put it in water, it only dissociates a little bit. It was like 2.5%. When you put it in pure water at a 0.1 molar concentration, it was only like 2.5% dissociated. But if you put it with strong base instead of just in water, it reacts completely. If I take this solution of benzoic acid and sodium benzoate and toss some NaOH in there, that NaOH, every single OH minus, is going to find a benzoic acid molecule and rip the H off of it to produce benzoate. It's going to react completely, okay? And so that's an important thing. We can prove that statement, but it sort of breaks the flow. Let's just accept it for now, and maybe as a separate small video we can prove the fact numerically that this is the case. But it's gonna react completely. When we toss in this example, let's have a 1 liter of this benzoic acid benzoate solution, and let's toss in 0.02 moles of NaOH. Okay, now we do a different kind of table. It looks sort of similar to the ice table, but look at it. It's got, instead of benzoic acid plus water, it's benzoic acid plus the OH minus. Okay, and instead of I, C, and E, it's labeled before addition. The situation that we had, this was the buffer at equilibrium, 0.1 and 0.1. Okay. And then the addition, what did we add? We added 0.02 moles of this hydroxide in the form of NaOH. Okay, and now as I say, it's going to react completely. That means every one of these hydroxide molecules is going to kill one of these benzoic acid molecules. You'll have 0.080 left over of the benzoic acid, and benzoate is produced in that process. It becomes 0.120. Okay, so just subtract the 0.02 from the one number and add it to the other. Okay. So that's the situation that we have after adding the 0.02. It changes the ratio of benzoic acid to benzoate. So here's just that same table again, just for reference. I want to do a calculation. Here's what the textbook authors do. Okay, they say after addition. Now that's my new input for a new ice table. Okay, that's going to be the initial line of my new ice table. Okay, and so here again, now we're back to the original equation. C6H5COOH plus water makes H3O plus benzoate. Okay, and the initial line has the results of the previous table. Often the previous table is called a stoichiometric, where you're just figuring out how much of each you have. That becomes the input for a new ice table. Okay, and then we do the minus x and plus x and plus x and add them up. And we treat it just the same as the calculations we've been doing for a long time. But guess what? When we do the calculation, put it in 0.12, we wind up with Ka is equal to the usual expression for Ka, 0.120 plus x times x in the numerator, and 0.080 minus x. We do the x is small approximation. Once again, it works very well. X is really, really small. It's 4.3 times 10 to the minus 5. Guess what? The concentrations, again, are just unchanged. Now, this time we had 0.080 and 0.120, but we did our ice table and we found out they didn't change from those values. They're still 0.080 and 0.120. Granted, minus x, but x is ridiculously small. It's 0.00043, okay? So subtracting that from 0.080 or adding it to 0.12 just makes no difference at all, okay? So these values that we found are, again, unchanged. Okay, the two again are the ice table. We didn't really need to do it. We get these same numbers that we would have predicted just on the basis of the stoichiometric table at the top. Okay, the H3O plus is the X in this calculation, and you can tell that from this expression from Ka over on the left. It's 4.3 times 10 to the minus 5, and that makes the pH 4.37, okay? But my point was, you don't really, the textbook writers always want to insert this second ice table, but it never does anything, right? There's no change as a result. So I wanted to say, well, let's just say we didn't do that. Suppose we didn't do that second ice table. Here again is the stoichiometric table where we calculate all the OH minuses react and so on. And we just take those values and put it into our expression for Ka. Ka is the benzoate, the C6H5COO minus, times H3O plus, times benzoic acid. Put in the values for benzoate, 0.12, times the H3O plus. That was the X before, but now I'm just calling it H3O plus, and 0.080 for the benzoic acid. Okay, rearrange that and you find what you found before, 4.3 times 10 to the minus 5, and the pH is 4.37. Okay, so we didn't really do that ice table. Inherent in that is that X is small approximation. But you look at this and you realize that H3O plus, that is the X, and it is really, really small. So in these buffer calculations, generally you don't have to do that second ice table. These are the values, just the same as before. It's interesting to think about a little bit about what happened as a result now of adding the 0.02 moles of OH minus. When we had the original buffer, 0.100 and 0.100 for benzoic acid and benzoate, the pH of that, if you recall, was 4.19, okay? So the original buffer, 0.1 and 0.1, was 4.19. Now, after we added this NaOH, it's 4.37. And you say, well, I thought you said it's going to hold the pH constant. Well, it is pretty close to, I mean, that is not a big change, right? It looks like it's a significant change, but think about it. If you put 0.020 moles of NaOH in just a liter of water, you would have OH minus would be 0.02 per mole, 0.02 molar. POH would be 1.7, and the pH would be 12.3, okay? So if you take 0.02 moles of NaOH and add it to a liter of water, the pH rockets from 7 all the way to 12.3. When we put that same 0.02 moles of NaOH in our buffer, it just went from 4.19 to 4.37. Okay, so it's a much, much smaller change. So that solution definitely helped to hold the pH more constant. It still did go up, however. It still did go up. And notice you added base and the pH went up. It only went up a little, but it did go in that direction, right? Basic solutions have higher pHs. So it did go in the direction of higher pH, but only a short ways. So those are good observations. Then I want to tell you about another equation, which is it's called the Henderson-Hasselbalch equation, and people associate it with buffers. It's very, very useful for calculating buffers and buffer solutions. It's really not different than what we just did, however. It's really just the expression for Ka that we just used, just in a different form, in log form. Okay, we take the logarithm of that equation. So let's do that. Here's the same Ka equation for the benzoate benzoic acid buffer. Let's make it a little more general, and let's write for the benzoate we'll write base, and for the benzoic acid we'll write acid. Okay, so there's the Ka equation now for just a generic acid-base pair. Okay, I want to get a relationship for pH basically out of this. So let me rearrange first. I'll rearrange to solve for the H3O plus. That's how that would look. H3O plus is Ka times acid over base. Okay, and then it'd be nice to get toward pH, right? So let's take the log of both sides. If you take the log of H3O plus, it's the log of what's on the other side, but then you use the properties of logarithms that the log of a product is the sum of the logs. So at the right here we have log Ka plus log acid over base. Then I'm going to take that, I'm trying to get to pH, right? pH is the negative log, okay? So I'm going to multiply through by a -1. Now I've got negative log of H3O plus is the negative log of Ka minus the log of acid over base. All right, so the thing on the left is just pH, the negative log of H3O plus. Negative log of Ka, we're going to start calling that pKa, all right? So the P has come to mean just negative base 10 log of what follows. So we're going to have pKa, later we'll also have pKb. It always means negative base 10 log of what follows, okay? And the other thing is negative log of acid over base. That's the same as positive log of base over acid. Remember, that's again properties of logarithms. So I can write it like this: pH is equal to pKa plus log of base over acid. That's the Henderson-Hasselbalch equation. Very useful, especially for buffers, and we'll see why. But You have to calculate your pKa. Ordinarily in problems, you're given Ka, and you have to calculate pKa from it. Just take the negative base 10 log. Here's that for that benzoic acid. Ka was 6.5 times 10 to the minus 5. pKa is negative log of that, which turns out to be 4.19. Okay. And then you can calculate away. For instance, that calculation that we just had was this. We had, let's see, the base was 0.12 and the acid was 0.080. Okay. And you can just put those directly into the Henderson-Hasselbalch equation. It's the pKa of 4.19 plus the log of 0.12 over 0.080. And it turns out to equal 4.37. And of course, it's the same number that we got before, calculating using the non-logarithmic version of the equation. Okay, so this Henderson-Hasselbalch equation is just the same, equilibrium expression for Ka that we've always been using, but written in a somewhat more handy form. And the fact that we can plug into it directly, put the 0.12 directly in there and the 0.080 directly in there, that comes from the fact that the values the values of the base and acid concentration in a buffer solution are typically just as you mix them. They don't change. You mix 0.1 and 0.1, you get 0.1 and 0.1. You add some base and it's 0.080 and 0.12, you can use those values directly in the Henderson-Hasselbalch equation. Inherent in that is that x is small approximation, but it's generally very, very, very good. Okay. So let's do, there's that same group, that the same values that we calculated before. Let's do a completely different example. Here's lactic acid. I don't know if got that transition. Here's lactic acid. Ka is 1.4 times 10 to the minus 4. And they give us the concentration of lactic acid, and they give us the concentration of sodium lactate. And we figured out that we can use those values directly, that the values in the buffer solution are going to be as we mix them. We do have to calculate pKa, easy enough to do that. It turns out to be 3.85. So we go directly to the Henderson-Hasselbalch equation, 3.85 plus the log of base, the lactate, over the acid, lactic acid. Do the calculation, it turns out to be 3.69. Okay. So pretty simple calculation. If someone asks you, well, what are the concentrations of the lactic acid and the lactate? Well, they're just the same as they were from their as mixed values. They're unchanged. You can prove that if you want to by taking finding the value of H3O plus. You could find it from the pH and show that it's a very small number. So it would be easy to do. I wanted to point out a couple of things about the equation. Notice that if the base is equal to the acid, like in that one example we had a little while ago, is 0.1 and 0.1, the numerator and the denominator within the log term in the Henderson-Hasselbalch equation, if those two are equal, you have the log of 1. Well, the log of 1 is 0, right? So if the base equals acid, in some situation, then the pH is equal to the pKa, right? If the base concentration is greater than the acid, then you'd expect the pH to be greater than pKa. And if the reverse is true, as in this example right here, let's see, the acid is 0.22 and the base is 0.15. So the base is less than the acid and the pH is less than the pKa. 3.69 is less than 3.85. So those are handy things to note. We'll do more with this, but it's best to do a few problems and kind of get used to it. So we'll leave it there for now. More to come, though. There's more with the Henderson-Hasselbalch equation.